Okay, I think you better. We're at the last session, and it's good that we will now hear something about Mendelian randomization. Actually, we've not heard so much about causal association. So from here. Just get right.
Hi, hello everyone. Very happy to be here, and thank you to the organizer for this organization of the session. I'm afraid I don't know much about the backgrounds of the audience, so I try my best to explain. And if you have any questions, feel free to stop me at any time. And today I'm going to talk about breaking the winner's curse in Mendelian randomization, or maybe just a quick introduction of myself. I am an assistant professor of biostatistics here at UC Berkeley in the School of Public Health. And this is a joint work with my collaborators, Xinwei Ma, he's an econometrician in UC San Diego, and also Chong Wu from Florida State University. Since I'm going to talk about Mendelian randomization, I want to show you this has been a very popular thing in epidemiology. This is the record counts I extracted earlier this year. So you can see the record counts from the Web of Science for Mendelian randomization has been increasing over the past decade. So what really is Mendelian randomization? So I'll start my talk with introducing what is Mendelian randomization and what Mendelian randomization can do for us. So this is a plot I want to investigate the effect of smoking on life expectancy. If you only look at the associations between whether you smoke and how long you can live, it looks like smokers tend to die younger. It certainly looked that way, but is there any causal associations between these two factors? We do not really know, because there are many factors hinders our understanding between these two factors. Well, for example, there are many confounders between smoking and shortened life expectancies. Smokers typically tend to drink more heavily and have a less healthy diet. And these less healthy diet can also lead to them to have a shortened life expectancy. From a different angle, when people become ill, they tend to give up smoking. So this may wrongly suggest their worsened health are actually due to the give up smoking. So there are some reverse causation issues we have to take into account. Well, ideally, we probably want to run a randomized control trials. Say we recruit 10,000 patients and we assign half of them to control, say they do not smoke, another half to smoking. And then we monitor their health for a long time so that we would know if their shortened life expectancy are really due to smoking. But this kind of randomized control trials are neither ethical nor practical. Fortunately, we've all been recruited into an experiment when we were born. So our genes are randomly inherited from generations to generations, and they are not confounded with any factors we have in our life. Our genes also decide how we sleep, eat, and also to some degree our smoking habits. For example, that we know that smokers carry one version of the gene is called ChRNA5, tends to smoke more heavily than those who carry a different version. So this means carrying ChRNA5 leads to probably more like a smoking tendency. So when we stratify patients, probably participants or like people according to which version of ChRNA5, we found out there's no association between their life expectancy and smoking. Between their shortened life expectancy and in non-smokers. So this means carrying this one particular version of a gene cannot actually lead you to have a shortened life expectancy. There means there's no association between carrying ChRNA5 and also shortened life expectancy. But when we measure the association between smoking and shortened life expectancy, and this is something we can observe. This just means the effects between smoking and shortened life expectancy must be kind of explained by carrying this version of the gene. So Mendelian randomization is the kind of approach is trying to incorporate genetic information and try to tell us about the factors influence our health. So this is just one motivating example. So we are trying to use something else only affect the treatment that does not affect the outcome to conduct causal analysis. In a more mathematical language, we can look at a causal diagram. In this causal diagram, we have a risk factor, say smoking, and Y here is the outcome. And we are interested in knowing what is the causal association between this risk factor and the outcome. So this parameter of beta is our interest, is our key parameter of interest. And because there are many unmeasured confounders U here, so I hope to use other genetic variants as instrumental variables to conduct causal analysis. So typically in our body, we have more than one gene. So this means we have access to G1 to GP, multiple genetic instruments. In this case, Mendelian randomization are hoping to use all this information to better estimate beta. How can we do this? In this causal diagram, I'm going to make 3 assumptions. So the first assumption is we want to use those genetic variants who are relevant to the risk factors. This means we only want to use this genetic variants GG, which are associated with a risk factor X. In other words, we want to use these causal pathways with gamma J does not equal to 0. The second assumption is that we want to use GGs, which are independent with the potential outcomes. With unmeasured confounders. And lastly, we also assume G is also blocked away from this potential outcome Y. So there's only one valid causal pathway, which are through G to X to Y. Under this causal diagram, of course, this is one of the basic causal diagram. There are also other issues we have to focus on. For example, like genetic pleiotropy. This means other causal pathways may not have a cross here. But this is really not the focus of this particular talk. So in this talk, I'm going to work with the simplified assumptions for Mendelian randomization. In this causal diagram, we can work with very popular structural equation models. So we can see the outcome Y can be explained by a linear combination of my risk factor as well as the unmeasured confounders U. So Y equals beta X plus theta Y of U, another noise term which is independent with everything. And then for the risk factors, so the risk factor can be explained by a linear effects of all the genetic variants plus the unmeasured confounders plus something which is also independent with everything. Once we have this equation in hand, these 2 equations in hand, again, our parameter of interest is beta, is the causal effects. So simple plug-in trick, we can just plug in the equation of X into the equation of Y. Let's see what happens. So by doing the simple plug-in trick into between these 2 equations, so we find out the causal effect of beta is simply the ratio between this big gamma J and little gamma J. So here in this causal diagram, the big gamma J are the measured associations between Y and the genetic variants. And the little gamma J are the measured associations between G and X. So when we take the ratio between these 2 numbers, we can have access to the causal effects. The question is, okay, it looks very simple. As long as I have these 2 ratios, I know how to estimate the causal effects. The question is where we can have these associations. Fortunately, in the past decade, the proliferation of genome-wide association studies give us access to these associations, these measured associations. Suppose for now, we have 2 data sets. One data set contains the measured associations between the genetic variants and the exposure variables. In other words, we have access to these gamma J heads along with its standard errors for all genetic variants. And then in another data set we call outcome data sets, we have access to the associations between the outcome and the genetic variants, and they are denoted as this big gamma J. Once we have this, we can say, okay, for each genetic variant, I can simply take the ratio between these 2 associations. So they're all like beta J's. Because we have so many different beta J's, we can always do a meta-analysis to combine them. So a very popular estimator has frequently used in Mendelian randomization is called inverse variance weighted estimator. As you can see here, I'm just doing a weighted combination of different beta J's estimated from different genetic variants. But there's a very small problem. The question is, what if some gamma J's are very, very small? This means some genetic variants are only very, very weakly associated with my risk factors. In this case, if we include those genetic variables as genetic variants as an instrumental variables, this will lead to our RIVW estimator very, very unstable because beta J hat is going to explode. The reason I want to start with this particular RIVW estimator is because it's so popular. So nearly in all Mendelian randomizations paper I saw report this estimator. So that's why I want to start with this one. Okay, so the question is here, I have a very, very small gamma J hats for some genetic variants. now some beta j hats are going to explode. A common practice has been adopted in Mendelian randomization is SNP selection. Very simple idea. Say I only want to use genetic variants, gamma j hats, when they are larger than some threshold, some significant threshold. I only incorporate J, variant J, as long as, say, my associations bypass some significant threshold. This is a very natural idea, right? Because I want to have those stabilized beta J hats. But this common exercise actually casts a winner's curse into our Mendelian randomization. It's very simple. Because gamma J hats are the associations measured with air. They're actually a random variable. They can differ across to different sample to different sample. This means when gamma j hat divided by sigma j is larger than lambda, does not mean in the population my gamma j is also larger than this lambda. And when this gamma j hat is actually larger than gamma j, this means our beta j hat is going to be underestimated. Once you underestimate beta j, the whole causal effect is going to be underestimated as well. That's why sometimes we report results from Mendelian randomization. Actually, the results you got, the causal associations you got, might be lower than the ones actually in the population. And this one is called, this phenomenon is called by the winner's curse phenomenon. And according to my reading, and this winner's curse phenomenon is known as one of the fundamental challenges in Mendelian randomization with summary data. In this talk, I just want to show you, okay, how severe is Mendelian randomization. I probably won't show you something in real data analysis for now. Let's start with a simulation study. This is a very commonly adopted simulation study in Mendelian randomization with summary data. They're very boring, so I want to skip them. So you can see my beta j, sorry, this is actually gamma j, it's a typo here. Actually follows a truncated normal distribution. So most of the genetic variants has no association between the with the risk factor, and only a small portion of them has association with the genetic variant, with the risk factor. And in this simulation setup, I want to show you how severe the winner's curse bias is. I will consider like 3 estimators in particular. So one of them you have already seen is called two-sample Mendelian randomization with RIVW. This means SNP selection and causal effect estimation happened on the same sample. So this two-sample Mendelian randomization estimator has some data double use issues. And because winner's curse is really caused by I'm using the same data for selection and estimation happening on the same sample, a very, very intuitive way of avoiding this winner's curse phenomenon is having a different, say, independent GWAS data for SNP selection. So this is something we call like a 3-sample Mendelian randomization estimator with inverse variance weighting. Very simple. So this means I want to have an like a independent data, independent GWAS, which is independent with exposure data set. And then on this data set, on this particular data set, also measures the association between the genetic variants and the risk factors. I conduct SNP selection. I want to know which SNP have a genuine association with the risk factors. And then on the rest of 2 data sets, I construct my original RIVW estimator. Well, this 3-sample RIVW estimator looks very, very nice, but in practice, finding a third independent GWAS is actually very, very hard. Oh, this might be because the GWAS are always done by meta-analyze, so they want to incorporate more and more SNPs, the largest SNP, the more data, as many data sets as possible. So finding a third independent GWAS to some degree can be very, very hard. Let's look at the simulation results. Now on this plot, I want to show you on the y-axis is the bias proportion, which is measured by the Monte Carlo bias divided by the causal effects. And then on the x-axis, I will show you the IV proportion around the cutoff value. So you can think about when more IVs are around the cutoff value, around a fixed significant threshold, more of them are going to be accidentally correlated with my risk factors. In this case, the winner's curse will be enhanced. 3 curves. So one curve, this red curve, is the 2-sample Mendelian randomization estimator. And the blue curve is the 3-sample Mendelian randomization estimator. And the green one looks perfect. So this is our estimator. So you can see from this results here, the difference between the 3-sample Mendelian randomization estimator versus the 2-sample one is really caused by the winner's curse because there is no difference between them. The only difference is actually selection for 3-sample MR estimator happened on a different sample. You can also see there is a small observation. There's a small residual bias in the perfect free simple Mendelian randomization estimator. So later on, I will show you the small residual bias is caused by the measurement error bias issues in Mendelian randomization with summary statistics. Now we have seen the winner's curse bias, and we have also seen free simple Mendelian randomization is not really perfect. Now in this talk, in the rest of probably like 10 minutes, I will give you a possible remedy to completely remove the winner's curse bias. Well, in genetic study, you might have heard winner's curse phenomenon for many, many times, and there are many, many approaches proposed to some degree to overcome this issue. But so far, according to my reading, no methods can completely remove the winner's curse bias. Every method can do a little bit bias correction, but once you do bias correction, valid inference becomes very, very challenging. The difference, so different from existing approaches, our approach is the one that fully breaks the winner's curse. There's no residual bias. And on the other hand, we can provide valid statistical inference with rigorous guarantees. Now let's take a look. What is the heuristics behind our proposal? Okay, so this is a boring page. I just want to show you why we have this small residual bias. So this is the RIVW estimator, which can be viewed as simply regressing the big gamma J on the little gamma J. So I will probably not go to detail here. I just want to show you there's a measurement error bias issue in Mendelian randomization estimator on the denominator. Ideally, if we want to have no bias in our estimator, the denominator should be measured with gamma J squared instead of gamma J hat squared. Just because in Mendelian randomization, everything is measured with randomness, everything comes from a random sample. Therefore, the denominator is actually much larger than the ones we ideally want to use. And this is really caused by we're using GWAS data from a random sample instead of from the population. So therefore, to remove this small residual measurement error bias in free simple Mendelian randomization is also very easy. So we just minus a term in the denominator to make this estimator a little bit larger. So this is how we actually remove the measurement error bias issue. So this is something not proposed by us. There's a very nice paper called the bias inverse variance weighted estimator. This is first discovered by them. So I just want to show you some intuitions. And our estimator inherits the same property as this particular estimator. Another thing I want to show you is the winner's curse bias. So where does the winner's curse bias comes is actually in the numerator. In the numerator, ideally, when the RIVW estimator has no bias, we want this gamma hat conditioning on selection have the same distribution as the original one. We hope that gamma J hat centers on gamma J. Well, just because the gamma J hat distribution have to be conditioning on selection, therefore the conditional distribution no longer follows a Gaussian distribution. So our key idea of breaking the winner's curse is to say, okay, since it have a distorted distribution, can we somehow restore its normal distribution with a correct center after selection? The thing is, we can. Our idea is to say, okay, since free simple Mendelian randomization estimator is free of winner's curse bias issue just because selection happened on an independent sample. So our idea is say, okay, I want to create independence. I want to create the independence between the SNP selection and parameter estimation. So the way we do it is to say, we don't do the original SNP selection procedure anymore. We want to do a randomized SNP selection. We want to create something fake, something like called ZJ, which is something we call the pseudo SNP risk association measure, ZJ, follows some Gaussian distribution. And the randomized selection procedure we do is say, we want to select a SNP J only if gamma J hat plus ZJ bypass some significant threshold. So this is a different selection procedure, but as long as your SNP has a genuine association with your risk factor, this won't actually affect your selection because gamma J is already very, very large. Yet a random noise is still going to be selected. And this is our randomized SNP selection procedure. You might also notice I have a tuning parameter gamma here, eta here. So our procedure is actually not very sensitive to the choice of eta due to the next step I'm going to introduce. So the first of all, I want to create a different kind of independence. And the second step, I want to create some independence. So the way we create an independence, say, here is the selection event. I want to screen out these weak IVs. And then I want to create an gamma J hat estimator, which is independent with selection. And also this initial estimator is also correctly centered on gamma J. So once we have created the independence between these two things, and we are ready to propose our final estimator. But before we do that, we have to say the initial estimator is something I construct. It's purely by construction by probability. In this case, it may not have a full efficiency. So we want to have more efficiency. We want to more efficiently use our data. Therefore, we have a second step. We want to use raw blackization by projecting the initial estimator onto the sufficient statistic of the selection event. So once we do this, gamma hat JRB is short for raw blackization, has the full efficiency, is also the variance, is also the estimator, which is unbiased with the minimum variance. So once this gamma J hat is constructed, this first of all is independent of the selection. Second of all is also centered correctly on gamma J. We can completely remove the winner's curse. Just to give you more evidence, you can see this is a histogram of our construction. So conditioning on selection, the blue histogram shows the distorted distribution of gamma J hat after selection, and the yellow histogram shows the raw black-west estimator, which have the correct center and also looks very, very normal. This means our estimator can completely break the winner's curse in two-sample Mendelian randomization. Once we have the raw black-west estimator in hand, we can just go ahead and propose our final estimator, which you can see here have the similar format as the RIVW estimator. The only difference is that we have replaced the gamma J with gamma J hat RB. Just because this raw black-west estimator is correctly centered, conditioning on you have already selected this particular SNP. We have also removed the measurement error bias issue by minus a small term in the denominator. This is our final estimator. Probably this is something all I want to talk about, and in theory, in statistical methodologies. And lastly, maybe I have one more boring page to show just because I come from biostatistics. This is our theoretical guarantees. So now you can see our RIVW estimator. Oh, the reason we name it as re-randomized IVW estimator is just because Mendelian randomization has one layer of randomness because everything is randomly inherited when we were born. Our genes are randomly inherited. And now our approach re-randomized the whole selection procedure to have two layers of randomness. So that's why we call our estimator as re-randomized inverse variance weighted estimator. So now this is our theoretical guarantee. We can show our estimator after appropriate scaling converges to a Gaussian distribution, and its variance can be consistently estimated. This is all for the theory. Just a little bit on demonstration in numerical studies. We compare our approach with, again, the two-sample MR and the three-sample Mendelian randomization. Also, another approach remove the measurement error bias issues. And then the last one is called RIVW estimator. So this just a few things to highlight in this results. So first of all, our RIVW estimator is consistent. Its consistency is comparable with a three-sample Mendelian randomization estimator. So it's generally free of the winner's curse bias issue. And the second thing I want to say, RIVW estimator among the ones we have considered in this particular simulation setup has the smallest variability with a high detection power. So you can see the power is very, very, very good. This is also quite intuitive. It's just because we have conducted selection, we screen out those important SNPs. So it's also probably not a surprise that we have a high detection power for our estimator. And lastly, our RIVW estimator has also efficiently used the information stored in the GWAS. Because we are free of the winner's curse bias issue, we can incorporate more and more SNPs into our analysis. Okay, so one more thing, this is a similar message I want to show you. Maybe lastly, since I have probably 2 minutes left, I think I want to show you a real data analysis we have done. It's something called same trait analysis. Same trait analysis is a very simple idea to test if our methods works in real data really well. In the same trait analysis, our risk factor and outcome are the same thing. So we just want to know, say, for example, if increased BMI causes the increased BMI. So this means the causal effects in real data is generally 1. And these two GWAS we use to calculate the associations between BMI and the risk factors are just taken from the IEU Open GWAS projects. They're really independent GWAS data sets. And we have another measurement is HDL to HDL. Does the increased HDL leads to the increased HDL? So the causal effects again equals to 1. In this case, we can find out our RIVW estimator. Our RIVW estimator among the ones which are under comparison are the only one give us the genuine with a true causal effects estimate, which actually obtains 1. So all other estimator tends to have a downwards bias, which is which is in line with our analysis we have saw earlier. Just as a quick summary, in today's talk, I have discussed the benefits of using Mendelian randomization to study causal effects. And we have also seen classical Mendelian randomization with summary data provides biased estimates just due to the winner's curse bias and also measurement error bias issues. And we have offered a simple remedy called Rerandomized inverse variance weighted estimator that fully breaks the winner's curse as well as the measurement error bias issues. And that's all for my talk. Thank you.
Thank you very much. Questions?
Yes.
Is this on?
Thank you, Jingshen. I have to say, this is the most clear talk I've heard about Mendelian randomization introduction part. Yeah.
Thank you.
And so I have a question regarding the independence. So
Yeah.
I think you have the slide showing that the estimator is independent of the selection.
Yes.
Yeah.
Yes. Yes. Here.
Yeah,
Yes,
right
this
here.
one.
So in
Yes.
the first bullet point, I'm just curious, why are they independent?
Yeah, that's something you can check in probabilities to calculate it. So first of all, these selection variable gamma j plus zj follows a Gaussian distribution. And the initial estimator, just gamma j hat minus zj, also follows a Gaussian
I see.
distribution. You want to check independence, just check their correlation.
I see, I see.
Right.
Oh, that's a very interesting construction.
Thank you.
Yeah, okay.
Yeah.
Other questions? Yeah.
Yeah, the theory is very good. Have you tried on like not just the beta should be one cases,
Yes,
more like
yeah.
smoking versus cancer, you know, more the traditional cases to see whether or not you're doing better?
Yes, we tried. We tried in the analysis, in real data analysis, we have two case studies. One is the same trait analysis.
Correct.
Another
You
one,
showed that.
yes, another one is BMI to COVID-19 severity. We also found out through our approach, the causal effect is actually larger. So the log-outs ratio is actually higher than the ones we usually believe.
Mhm. So on average, you get more power. Is that
On
fair
average,
to
I
say?
got more power, yes.
Yeah.
Thank you.
Thank you.
So at this meeting, we have discussed multi-ethnic cohorts.
Yeah.
So is that something you think you can improve on if the causation is not the same in different parts of the cohort, for example, with
I have to,
COVID?
yeah, I have to apologize for my ignorance. I don't know what is multi-cohort study.
I mean, if you have a mixture of Caucasians, Europeans,
Yeah.
with people from elsewhere in
I
the
see.
world, from Asia and
see.
so on. So
That's a very
I mean,
interesting
it's a
direction,
sort of
yes.
goal in precision medicine
Yes,
to treat all ethnicities
Yes.
in a good way.
Yes, I think I understand part of the question.
Mhm.
I think that's a very interesting angle. But one thing is we haven't saw any Mendelian randomization approach works for multiple populations. So that's something worth investigating.
Yeah.
And on top of that, of course, there's a winner's curse bias component and something probably we can improve further.
Because I think potentially your approach could maybe
Maybe
do
Thank
something
you.
in that space where MR has not
Yeah.
been able to work.
Thank you. Thank you for the support.
Other. But great, and thanks again for this very clear talk. That's what we need at this point in the meeting. So.